All right, we're here for AP Physics Simple Harmonic Motion problems. Going to take a look at problem number 4 here. A particle moving along the x-axis in simple harmonic motion starts from its equilibrium position, the origin, at time 0 and moves to the right. The amplitude of its motion is 2 centimeters and the frequency is 1.5 hertz. Show the displacement is given by this equation. So here we go. So just kind of jotting some stuff down here. You would say, let's see here. We know that it starts off moving to the right, right? And it starts at the origin at equilibrium. And it starts off moving to the right. Let's see here. We know that the amplitude is 2 centimeters. So that's 0.02 meters. And so it's going to oscillate back and forth then from 0 to 0.02 to negative 0.02, right? Let's see here. And we know that the frequency is 1.5 hertz. So I'm going to say frequency is 3/2 hertz. Okay. And we want to write the equation of motion, the position for it. And so you would say, well, I know that the general formula is that position is A times, and you can use cosine or sine. Since we're starting at time 0 at equilibrium, it makes sense to use sine. And in fact, that is the function that they're giving us. So that makes sense. So A sine of omega t plus phi. All right. We're going to make phi 0. We're going to start at 0. So we don't want a phase shift. Okay, so that's easy. So that goes away. You say, I know that the period is equal to 2 pi over omega, the angular frequency. And since we know that that's equal to 1 over the frequency. Now, this value they gave us, again, that's the frequency, not the angular frequency. Okay, hertz is again per second. I know that is actually, well, anyway, just moving on. That is actually the same units as for omega. So you just have to be really careful when they tell it to you. They said frequency, not angular frequency, so I know I want F. So in other words, rearranging this then, you say that frequency, that 3/2, you say, rearranging this, we'd have that frequency is 2 pi over omega, omega over 2 pi. So that 3/2 is omega over 2 pi. So rearranging this, you would say that omega is 3 pi. So that's what's going to go in there for omega. And the amplitude is 0.02. So you'd say, hey, yeah, my position is going to be 0.02 sine of 3 pi t. Okay. And in fact, that is what they have here. Okay. And they write it as centimeters, but 0.02 meters, yeah. Okay. So that's part A. Part B, determine the maximum speed and the earliest time at which it has that speed. Now, there's a couple ways of doing it, but we could do it like an energy calculation, for example. But the fact that they already gave us this position equation, it's so easy to just get the velocity equation right away by taking the derivative. So by saying that the velocity, you say, hey, that's just going to be dx dt. So you say, let's take the derivative. So that'll kick a 3 pi out. So I'll have 0.02 times 3 pi. Derivative of sine is cosine. And so you say, now wait a minute. I remember that any cosine function, it varies in size from -1 to +1. So the maximum value is 1, which means the maximum value of this function is just 1 times this coefficient in front. So the V max is, in other words, just the coefficient in front there of the trig function. So you say, hey, that's going to be 0.02 times 3 pi. In my calculator, you would say 0.02 times 3 times pi. Okay, and I get 0.1885 meters per second. Okay, because I switched to meters. In centimeters per second, that would be like 18.85 centimeters per second. Okay, part C. Now that we'd like to know Determine the maximum acceleration in the earliest. Oh, I forgot to find. I just want to know the earliest time when it has that acceleration. So you say, well, it's going to get maximum when this is maximum, right? So I just need to know, well, when is the cosine function maximum? You say, well, cosine is maximum at time 0, but they want a time greater than 0. So you say, well, the next time it's at maximum cosine function is when you get to pi. So you're like, what time t there would give me pi? So I'm saying 3 pi t is pi. Okay, well, that'll happen when t is a third of a second. So that's the first time after time 0 where we'll be at max speed. Okay? Yep. And again, it makes sense. We're starting at equilibrium, right? And you have max speed at equilibrium, right? 0 speed at the amplitudes. That makes sense. Okay, let's go to part C. So it's going to be here, and then it'll be anyway. The period is 2 pi over omega, right? And we figured out the omega was 3 pi. So 2/3 is the period. Halfway through a complete cycle, right, would be when it got back to equilibrium again at 1/3. Anyway, moving onward, back to part C. Part C says determine the maximum acceleration the earliest time when it has that acceleration. So you say, well, to find A max, I'm just going to take the derivative of the velocity equation. So I'll just say if I took dv dt, that would be A. So I'm going to take the derivative. Let me swap colors here. The derivative of this function, right? So taking the derivative, it would kick another 3 pi out. So I'd have 0.02 times 3 pi squared now, right? And then derivative of cosine is negative sine. And I still have that argument in there, 3 pi t. All right. Again, the maximum, that sine, you see there's no variable in here. Time is here. The maximum, what makes sine maximum is when it's at pi over 2 is the first time it's at max, right? And so you say, because it starts off at 0, at 0, right? So it's got to get a quarter cycle through to the pi over 2. And so you say, okay, well then I want 3 pi t to be pi over 2. So again, this coefficient in front is going to be the maximum, and then it's going to reach maximum when t is 1/6 of a second is when it'll reach max. What will that max be? It will be 0.02 times the quantity 3 pi squared. 0.02 times the quantity 3 times pi squared. And you say, hey, that's 1.777 meters per second squared. So that's our maximum acceleration, and we reach it at 1/6. Okay, now technically you said it's going to be a negative there. I'm assuming they want the negative, the largest magnitude acceleration, right? Because if you think about it, right, here we got our positive direction to the right. It's going to start off going to the right, and you say when it's at the amplitude, that's where, remember, the force in a simple harmonic oscillator has to vary linearly with distance from the equilibrium, right? So when I'm at maximum displacement, that's when I'll be at maximum force. And the force is always trying to push you back to equilibrium. So it'd be in the negative direction. So that makes sense that I'm getting a negative out when I'm at that max first amplitude. And again, the time for a whole cycle, we figured out that the period, if the frequency is 3/2, the period is 2/3. And so we said, well, 1/2 the cycle when I got to here was at 1/3. Half of a third is a sixth, right? That's when I'm at the extreme here. So a 6 second makes sense. All right, that's part C. Part D says determine the total distance traveled between 0 and 1 second. Well, we know that frequency is 3/2. Period is just the inverse. The total time for a cycle is 2/3. So of a second. So for 1 second, you say 2/3 is a period. I recognize that it's 1.5 periods. In a period, we would start here, we would go to here, and then back to here, right? We're back to that starting position, doing the same thing, going to the right. Okay, we're at the start, at the equilibrium, going to the right, equilibrium on our way to the right. That's 1 cycle. Now we're going to do another half a cycle. So we're going to do this and then this again to here. So you say, okay, how far is that? Well, every time every excursion the thing makes from equilibrium is 0.02 meters. So this is 0.02, 0.02, 0.02, 0.02, 0.02, 0.02. 1, 2, 3, 4, 5, 6 times 0.02. So you say, hey, the maximum distance, the total distance we went was 6 times 0.02. Right? So that's going to be, 12 centimeters. It's going to be 0.12 meters. Okay? And there's my answer for that part. All right? And that's problem 4.